So what we're going to be doing is mostly evaluating integrals of this sort of type, where we're integrating either from minus infinity to infinity or from 0 to infinity some function of x. We'll do some other integrals as well, but mostly they fall into those two categories. And we're going to do it by using the residue theorem. And what we do each time is most of the time we consider an integral of f of z dz around a closed loop gamma. Okay, and the idea is that we choose the shape of this contour gamma so that one of the sides, part of gamma, is the integral we want. So, for example, here, and we end up sort of choosing the limits to be, for example, in this case, minus r to r, and then take the limit as r goes to infinity to get the integral we actually want in the end. So we end up choosing one part of the contour to be the integral we want, and then the other part will be something which we know the answer to. Now, in cases like this, it turns out that we can show that this integral along here, the whole integral gets wider and wider. In fact, the integral along here, if this integral exists, will tend to 0. Same sort of thing here. This is the integral we want. It will turn out to be a multiple of the integral we want. So this along here will end up giving us the integral we want, I. This along here will end up giving us a multiple, we'll say alpha times I, the integral we want. And then this bit here, along here will turn out to be 10 to 0. So we end up saying, well, okay, this thing here then ends up being the integral we want, or I plus alpha I, whatever. So that's the left-hand side. And then the residue theorem will tell us that this is equal to 2 pi I times the sum of the residues inside the contour. So we always need to know where are the poles inside the contour. So we tend to draw things to explain what we're doing. We always draw what's called the contour on the complex plane and show the direction of the contour, show where it goes, what the shape is, and also it's a good idea to indicate where the poles are, just to be sure. Now, what can happen, the residue theorem really applies if there's a finite number of poles, finite number of singularities inside the contour. What can happen is that for some functions you want to integrate, there are an infinite number of singularities, infinite number of poles, and this can happen in particular if you've got things like exponentials or hyperbolic functions which have imaginary period. Then it's quite possible that you have sort of series of poles going up forever. So then you need to think of a different shape, and the appropriate shape then is a rectangular contour, and in that case the integral you want is along here. You choose this height of the contour so that the integral along here is a multiple of the integral you want, and then it will turn out that these integrals along here will vanish as r goes to infinity. And finally, if the function f has a branch cut, this can be very useful, because what you end up doing is the integral you want is along here, but because you've got a branch cut here, this value is completely different from this value, and it would generally turn out to be the case that this integral along here is not the same as this integral along here. It would just be a multiple of it, where alpha is not minus 1. So again, you can find the integral you want, and this integral here will tend to 0, hopefully, as r goes to infinity. So that's a rough idea of what we'll be doing. There's some other sort of little special cases that we'll look at, such as sometimes you can get a pole actually on the contour itself. So we'll look at that in more detail a bit later.